Hello and welcome. This is going to be the two envelopes paradox. Now, the original paradox has a certain error in the reasoning, which is really fun to look at. But this version of the paradox is actually more awesome because we're gonna fix the original paradox in a way to make it actually happen. We're actually gonna make the paradox happen this time. So we're gonna be given two envelopes. We're only going to be allowed to look inside one of them, and there will be some amount of money in that envelope, and we're given the option if we want to switch to the other envelope, which is going to have an unknown amount of money in it. So if we switch, we might make more money, or we might lose money. That's sort of the dilemma that we're going to be put in. So the way it's going to work is one of the envelopes is going to get 2 to the power n dollars, say like $8, and the other is going to get twice that much, say $16. And then the two envelopes are going to get shuffled, and we're only going to get a look inside one of them, and then we have to decide if we want to switch to the other. So if we see $8 in this envelope, say, it could be that the other envelope has $16, or it could be that the other envelope has $4, because one of them is going to have twice as much as the other, so it's either 8.4 or 8.16. And we're going to actually set up a probability distribution for this. So the way it's going to work is we're going to first decide the probability that the smaller amount of money shows up. So for example, the probability that we'll put $1 as the smaller amount, so we'll have $1 and $2, is going to be 1 over 3 times 2 over 3 to the power 0. So you see 2 to the power 0 is 1, so if the probability that the smaller amount equals 1 is 1/3 times 2 over 3 to the power 0. What about the probability that the smaller amount will be $4? Well, the probability that the smaller amount is 2 to the power 2, which is $4, is going to be equal to 1 over 3 times 2 over 3 to the power 2. And then always, whatever the smaller amount is, we're going to put double that amount in the other envelope. So, for example, I'll give some examples soon to kind of make it click a little more. So, say you are given an envelope and you observe that the amount is 2 to the power n dollars. Well, you'll know that you're in either one of these two situations. It could be that you're looking at 2 to the n dollars and the other envelope has 2 to the n plus $1. In that case, the smaller amount of money is 2 to the n dollars. Or it could be that you're looking at 2 to the n dollars and the other envelope has 2 to the n minus $1. In that case, the smaller amount is 2 to the n minus $1. By the way, the probability of $1, $2 is 1/3. The probability of $2, $4 is, 2/9. The probability of $4, $8 is 4/27. It kind of proceeds in that kind of way. So when we see that we have $2 to the n dollars in our envelope, if we're in this situation and we decide to switch, we're going to make 2 to the n dollars. But if we're in this situation and we decide to switch, we're going to lose 2 to the n minus $1. For example, if this is $8 and we switch to $4, we lose $4. If this is $8 and we switch to $16, then we make $8. So what we want to find is, given that we're looking at 2 to the n dollars in our envelope, what is the probability that we're in this situation versus what is the probability that we're in this situation? Because it has to be one of these two, right? So let's take a look at this. So let's think about the probability that the smaller amount is 2 to the n dollars, which is this situation here, right? 2 to the n is the lesser amount between these two, given that either the smaller amount is 2 to the n dollars, or the smaller amount is 2 to the n minus $1, which would be this situation. So in other words, this probability here is the probability that we're in this situation, given that we're in one of these two situations. So what we are going to do here is use Bayes' rule. So the way that works is that the probability of something given something is going to be the probability of this and this, right? Probability of this and this, so s equals 2 to the n and s equals 2 to the n, or s equals 2 to the n minus 1, divided by the probability of this, because it's kind of like saying, what's the probability that both of these happen? Out of all the possible worlds where this is guaranteed to happen, because this is the given. So we're dividing by the probability that the smaller amount is 2 to the n, or the smaller amount is 2 to the n minus 1. Now, think about logic for a second here. S equals 2 to the n and s equals 2 to the n, or s equals 2 to the n minus 1. That's kind of like saying the probability that it's 8 and it's 8 or 4. Well, the probability that it's 8 and it's 8 or 4 is just the probability that it's 8, because, well, it definitely can't be 4 if it's 8, and this is, you know, think about it like propositional logic, right? So I can just simplify this top part to just the probability that s equals 2 to the n power. And then the bottom part is the probability that s equals 2 to the n, or s equals 2 to the n minus 1. And these are mutually exclusive, so I can just add them together. So that's the probability that s equals 2 to the power n plus the probability that s equals 2 to the n minus 1. Now, given the probability distribution, that formula we had earlier, right? Right, the probability that s equals 2 to the n is 1/3 times 2 over 3 to the power n. So the probability that s equals 2 to the n is 1/3 times 2 over 3 to the power n. And then this is the probability that s equals 2 to the n, which is going to be the same thing again. And this is the probability that s equals 2 to the n minus 1, which is going to be 1/3 times 2/3 to the power n minus 1. Now I get a lot of nice cancellation here, right? Because this cancels with this, sort of. So basically the 1/3s all cancel out, and the 2 over 3 to the n cancels with the 2 over 3 to the n, cancels with the 2 over 3 to the n, but I am left with the 2 over 3 to the negative 1. So I'm going to have 1 here, 1 here, and then the 2 over 3 to the power negative 1 is going to take the 2 over 3 and flip it to a 3 over 2, so that's where that 3 over 2 comes from. And if you simplify this, you'll get 2/5. So what that means is that if we are, if I can find the, oh my gosh, how am I, is it underneath? Sorry. So that means that if we see 2 to the n dollars in our envelope, we know we're in one of these two situations, there's a 2/5 probability that we're actually in this situation. So there's a 2/5 probability that switching envelopes will gain us 2 to the n dollars, right? So 2 over 5 chance that we'll gain 2 to the n dollars. Now, the probability that we're actually in this situation is just going to have to be the rest of the probability, right? So if it's not the 2/5, it has to be the 3/5. So there's going to be a 3 over 5 chance that by switching we'll lose 2 to the n minus 1 dollars. So the question is, should we switch? Well, let's see what the average is. So 2 over 5 times 2 to the power n, that's going to be if we sort of win by switching, plus 3 over 5 times negative 2 to the n minus 1. So that's going to be how much we would lose if we're in the losing scenario, multiplied by the probability that we're in the losing scenario, added by how much we would win if we're in the winning scenario, multiplied by the probability of being in the winning scenario. And if you actually do the math here, this is going to be, you know, you can do the math and it actually comes out to 2 to the power n over 10, which is a positive number. So, for example, if we observe, oh, I don't know, $1,024 in our envelope, then by switching, we should gain on average $1,024 divided by 10 amount dollars. So 1,024 divided by 10, that's what, I don't know, $102.40. So we'll win $102.40 on average by switching. Even though, did I not say that originally the two envelopes were shuffled so that you don't know which one is which? So here's my question to you. Is this argument a good argument? Is it really best, no matter how much money you see in your envelope, to switch? Or is there something about this argument that, you know, maybe like the math calculation is correct, but the reasoning, you know, the argument to switch, there's something wrong with that argument to switch, and in fact it doesn't matter because you simply don't know which envelope is which, right? You don't know which one's which, it doesn't matter, it's, you know, it's all just grab one randomly and that's the best you can do. I want to hear what you think. I'm not going to give my opinion in the video. It's up to you. Maybe I'll comment my opinion or something, or my view, but hope that was interesting. Also, if you have any questions, feel free to ask, and yeah, take care.